For the afternoon session. The first speaker is Daisuke Ikegami from Tokyo University, who will talk about universal Baire subset.
Thank you very much. Can you hear me?
Yes.
Okay. So first, I'd like to thank the organizers of the conference. Yeah. Actually, I've been sick these days, so I haven't attended most of the talks. But I guess it's been a great conference. But anyway, yeah, and thank you for coming here, to my talk. So today I would like to talk about universally Baire subsets of 2 to the kappa. Kappa is any infinite cardinal. So let me just introduce what are universally Baire sets of reals first. So universally Baire sets of reals are some sets of reals with special properties, and it ties many branches of set theory in this way. For example, if you have large cardinals, the more large cardinals you have, then actually the more generic absoluteness, the more statements become generically absolute. And then the more complicated sets of reals become universally Baire. And also, many countable iterable structures have iteration strategies which can be coded by universally Baire sets. And universally Baire sets are all Lebesgue measurable and have the Baire property. And if you have large cardinals, then they are determined. So universally Baireness is really one of the key notions to connect these topics of set theory. And the goal of this project is to generalize the notion of universally Baire sets. And in particular, we'd like to discuss the universally Baire sets for subsets of 2 to the omega 1 and under large cardinals and strong forcing actions. And then we would like to get a deeper understanding of the theory of subsets of omega 1 or sets of subsets of omega 1. But today we only introduce the notion of universally Baireness for subsets of 2 to the kappa, or the power set of kappa, where kappa is any infinite cardinal, and develop its basic theory. So, yes. Let me just, first start with some basics. So, from now on, X will be always compact half-dose space. And let me introduce some basic notions. So, if you have a subset of X, let's say A, then A is nowhere dense. I guess most of you know. If A is disjoint from an open dense subset of X, so A is very small in the sense of topology, and A is mega if A is the union of omega many or countably many nowhere dense subsets in X. Then, the point of having this notion is actually the whole space X is not mega if you have compact Hausdorff space. This is Baire category theorem. And using this fact, you can make sense of the non-trivial notion of the Baire property. I guess most of you know. But if we have a subset A of X, then A has a Baire property in X. If you can find a open subset of X, which can be which approximates the original set, modulo mega set, in this sense. So, if you can find an open set such that the symmetric difference between U and A is small, in the sense of meganess. And then I guess this is one of the basic regularity properties. And so, for example, open sets all have the Baire property, and Borel sets have the Baire property. And if you consider the Cantor space, 2 to the omega or power set omega, then you can introduce the universally Baire sets of reals using this Baire property and compact Hausdorff space. So, well, this is one of the definitions of universally Baire sets. So if we have a set of reals or a subset of the Cantor space, let's say A, then A is universally Baire if you take for any compact Hausdorff space X and any continuous function from X to the reals, then the preimage of A has a Baire property in X. So this is a definition. And there are more definitions which are equivalent to this definition. So, well, the first thing you can notice is every universally Baire set has a Baire property, because if X is the 2 to the omega and F is the identity function, then this F inverse A is just A. So every universally Baire set has a Baire property. And the second item is a bit more non-trivial, but well, if you have a universally Baire set, then it's always Lebesgue measurable by looking at the Stone space of random forcing, actually. And it's classically known that every sigma 1 set is universally Baire in ZFC. Yeah. And you cannot go beyond in the sense that actually if B is equal to L, then there is a delta 1, 2 set without the Baire property. Well, actually, yeah, which is not universally Baire. But if you have large cardinals, then you can go beyond sigma 1 set. Namely, if you have proper class many wooden cardinals, then every set of reals in L over R is universally Baire. And every universally Baire set is determined in the sense of Gale-Shot games. Yeah. So universally Baire sets have very nice properties, and many complicated sets become universally Baire if you have large cardinals. Okay. So these are the background of universally Baire sets of reals. Any questions so far? No? Okay. So now we would like to introduce the notion of universally Baireness for subsets of 2 to the kappa. And let me do some preparation for the generalization. So from now on, B will be always a complete Boolean algebra. Then we'd like to introduce the Stone space of B, which is a collection of Ultor filters on B. And this collection is topologized by the sets of this form, so OB. So it's a collection of all Ultor filters on B, picking up this small b. And this is a basic open set. And yeah. And I guess this space is known to many people, and most basic property of this space is compact Hausdorff. Yeah. And yeah, we will consider this space, this kind of spaces, mostly when we consider universally Baireness for subsets of 2 to the kappa. Okay. So now we are ready to define the notion of universally Baireness for subsets of 2 to the kappa. So from now on, kappa will be always infinite cardinal. And we will identify power set of kappa with 2 to the kappa, which is just a set of functions from kappa to 2. And we will topologize 2 to the kappa as the product space of the discrete space of this. And I guess many people are working on descriptive set theory in 2 to the kappa or kappa to the kappa nowadays for not with this topology but bounded topology or something else. And there is a reason why we need to discuss this product topology in this case, and it will come out later. So when we introduce the universal bareness and try to generalize the basic properties of universal bareness, it's better to stick to the product space when we consider the topology of this space. And now we just generalize the notion of meagerness and Baire property to kappa meagerness and kappa Baire property. So if we have a topological space, compact Hausdorff topological space, and then if we have a subset of X, then A is kappa meager. Well, it's just if it's just a union of kappa many lower than subsets of X. So we just replace omega with kappa here. And A has a kappa Baire property in X if you can find an open set U such that well, this open set approximates A modulo kappa meager sets. So just natural generalization of meagerness and Baire property. Okay. Any questions so far? Okay, and then one thing you can notice is, so the Baire category theorem allows you to prove that the whole space is not meager if X is compact Hausdorff, but in case B is complete Boolean algebra and stone space, if X is stone space of B, then this is compact Hausdorff, and X is kappa meager if and only if the forcing action for B with kappa many dense sets fails. So we don't know, I mean, depends on B, what kind of B we consider, whether the stone space of B is kappa meager or not.
What's the forcing axiom for B?
So if we have kappa many dense subsets of B.
Or whether there's a generic for those?
Yeah.
Subsets?
And if you think about this property, then, well, if the whole space is kappa meager, then every subset of X has a kappa Baire property because it's approximated by the empty set or the whole space. So if the whole space is kappa meager, so this property does not make sense. Well, it's a trivial property. Okay. And now we introduce the notion of B bareness. So if B is a complete Boolean algebra, then, well, if you take any A, which is a subset of 2 to the kappa, then we say A is B Baire if you take any continuous function from the stone space of B to 2 to the kappa, then the preimage has a kappa Baire property in stone space of B. So, well, in the definition of universally Baire sets of reals, actually, you took any B, any compact Hausdorff space instead of this stone space of B, and you consider kappa to be omega, but this is just the generalization of such property for each B, stone space of B. Then, well, as we have seen, if X, so the stone space of B is kappa meager, then well, any subset of 2 to the kappa is B Baire because this any subset of stone space will be well meager. So this property also becomes trivial if forcing action for B with kappa many dense sets fails. And then now we just generalize the notion of universally bareness to those for subsets of 2 to the kappa. So you look at the collection of complete Boolean algebras. and you take any subset of 2 to the kappa, let's say A, then A is universally bare in 2 to the kappa with respect to gamma. Let's say UB gamma kappa. If A is B bare in 2 to the kappa for all B inside gamma. Okay. So what this is, we'll see why this is a generalization of universally bare sets of reals. So let's look at some examples of this notion. So if kappa is omega, then if gamma is the class of all complete Boolean algebras, then UB gamma kappa sets are the same as universally bare sets of reals. So this means that, well, in the case of universally bare sets of reals, you consider all the compact Hausdorff spaces and then take a continuous function from the x to the reals. But if gamma is the class of all complete Boolean algebras, then you consider only stone space of those spaces and then take the continuous function preimage of the stone space of B to the reals. And those two things coincide when you consider, universally bareness or B bareness. So this is a generalization of universally bareness for sets of reals. And some more examples. If kappa is omega 1, and if your kappa is the class of all complete Boolean algebras, and if you look at C omega 1, which is just a forcing which has omega 1 many coreals, and assume if forcing axiom for C omega 1 holds, then no well order on 2 to the omega 1 is UB gamma kappa. Okay. On the other hand, if you restrict your class of forcings in the following way, then you can find some UB gamma omega 1 well order. So these examples 2 and 3 basically say it depends on which class of forcings or complete Boolean algebras you choose, then the notion of universally bareness certainly changes. So let's look at the third example. So if kappa is omega 1 and gamma is the class of complete Boolean algebras such that B force is BPFA, then if you have proper class many Woodins and BPFA in V, then there is a result by Caicedo and Velichkovich, which gives you a delta 1 definable well order of 2 to the omega 1. Delta 1 definable in this structure. And that's absolute in among the models in models of BPFA. And using this kind of absoluteness, you can get universally bare well order or universally bare. Yes. So it depends on the class of forcings and which cardinal you talk about when you discuss universally bareness. Okay. Okay, so the next one is, there are many definitions of universally bareness which are equivalent, and one of the handy ones is tree representation. And so let's see. So this is due to Fermat Woodin. So if you have a set of reals, then A is universally bare if and only if for any complete Boolean algebra B, there is a set and trees such that you get A is the first projection of this, the set of passes through this tree, and this tree is basically complement in the generic extension. I guess most of you know what trees are, but let me just introduce. So if you have a set, then y to the less than omega is just a set of all finite sequences of elements of in y, and then if a subset S of y to the less than omega is a tree, if S is closed under initial segments. And then you can introduce this the set of all passes through S, which represents closed sets in y to the omega. And you can take the first projection of this set. So in this way, so by looking at the first projection of the set of infinite passes through S tree, you can get this kind of absolute tree representation. So the point is, you can represent A by this tree, and you get the complement. You can represent the complement of this set by another tree in the generic extension. And by generalizing the notion of trees, you can generalize this tree representation. And yeah, this way. So let's say, so let me give you some notations, just basic ones. So if for any small b in B, then B restricted to B is this. And then if you have a complete Boolean algebra such that this kind of forcing axiom holds for any small b in B, then A is B Baire in 2 to the kappa if and only if there are some notions of trees with the same property, corresponding property. And yeah, it's just the same theorem. And let me just introduce what this is. So for that, we need to introduce more notations. So let's look at first. So this bracket kappa to less than omega, kappa to the less than omega is a collection of all finite subsets of kappa. And then for set y, this is Kuhnen notation, I think. If you look at, yeah, this fn kappa y is what set of all functions, finite functions to y. Then if you have a set y, then you can introduce this tree kappa, which is a subset of this fn kappa y. So it's a collection of all finite partial functions from kappa to y, which is closed under initial segments. And then you can also introduce the notion of infinite paths, the set of infinite paths through this tree, by looking at the kappa sequences of elements of y with this in this way. Okay. So in this way, you can generalize the notion of trees and then get the equivalent tree representation for universal bareness for subsets of 2 to the kappa. And for this tree representation, you need to consider that the space is a product space, not the bounded topology. Okay. And you can also get the characterization of universal bareness by looking in terms of generic absoluteness. So basically, what if it's too long to read, but so you can get some characterization of universal Baire sets in terms of using generic absoluteness and stationary tower correctness. And you can also generalize this by changing only the red parts are the different. So you can characterize UB gamma kappa sets by changing only red parts. So basically, you look at instead of looking at countable stationary tower forcing, you look at stationary tower forcing, which generates a generic embedding of critical point kappa plus. And in this way, you can get the corresponding characterization of universal Baire sets. Okay. And there are many connections between iterable structures and universal Baire sets. And one of them is probably the basic one is this. So if you have proper class many Woodins and some assumption under in a model theory, generic nice UBH, then if you have any countable elementary substructure of B and collapse it, then you get iterable structure M, which is witnessed, whose iterability is witnessed by an iteration strategy coded by an universally Baire set of reals. And this can be also generalized when kappa is equal to omega 1. And if you look at gamma 0, such that gamma 0 is a class of all B, such that this kind of forcing axiom holds, then with the same assumption, if you look at the elementary substructure of B of size omega 1 and collapse it, then you can get an iteration strategy for this, which can be coded by this kind of universal Baire set. Okay, that's it. Thank you very much.
Any questions?
So you said that using the strict product topology rather than the bounded topology is important for this characterization of universally Baire.
Yeah.
Can you give something of the flavor of that? Is it
Yeah.
compactness or?
So basically, there is a connection between continuous functions from the stone space of B to 2 to the kappa, and B names for a subset of kappa. Yeah, so when kappa is equal to omega, this correspondence is between nice name for real and continuous function from the stone space of B to 2 to the omega. And if you, it's a very full, nice correspondence. And to prove this kind of characterization, you need to translate the language of topology into the language of forcing and vice versa. And for that, for this correspondence, you need to look at product topology. And this correspondence fails if you look at the bounded topology. For example, when kappa is omega 1. But if kappa is, for example, regular, then if you look at only less than kappa closed forcings, then this correspondence is still alive. So if you want to restrict yourself into the class of less than kappa closed forcing, when kappa is irregular, then it could make sense to look at this kind of notion.
If not, let's thanks again.